Mhm. Resume share. Good morning, everyone. So first of all, I am thankful to the organization of this ICACC to Tech 2023. So I'm again, first of all, congratulate the BM Institute and the Shri Vivekanand Group Institute Banur for organizing such a wonderful event. So every year BM College organize this type of events. So it is my good luck to be part of some of them. So I'm also gratitude to Professor Harish Mittal, Dr. Vijay, Dr. Sorry, Vishal, Dr. Vishal, Dr. Puneet, and everyone for inviting me. So today's my topic is identification of disease severity level in rice plant using convolution neural network. Actually, if we will talk about the population of the world, so it is near about 7.7 billion at present. And then in within 30 years, it will go up to 9.7 billion, which is a 2 billion increase in near about 30 years. And it will be 11 billion in 2100. And why I'm telling you this high population, because half of the population consume maximum part of their calories or take their calories from the rice. So this is the requirement of the total rice. And rice plants are there are chances that if we will don't take care of our these plants, then 20 to 40% will be wasted due to the disease. So at present, there are government agencies or private technicians or experts which try to find out from their experience whether there are chances for the disease or whether the plant is having any disease or not. But what we are trying to do, we are using CNN to find out whether we can automate this process to find the disease in the rice plants. Not only we are doing to automate the find out the rice plants, so we are also doing to find out the severity level, which was not done by any researcher till date. A part of it, we are also trying to find out whether one plant is having multiple disease. Maximum research in this area is on the leaf, whether the leaf is having disease or not. But we are trying to find out the multiple areas of the plant. Next. Right. This next slide, please. Yes. So the content of my today's talk will be introduction, then objectives, then flow charts, then the workflow diagram, and the finally the sum of the results. The results are in the same shape of some application. So we have developed an app or application in which we have tried to automate the process. As I was telling that it is defined as any problem with plant that leads to reduction in the appearance. So an impossible task of for the farmers to survey the vast farmlands daily. And then the crop loss is in production of 20 to 40%. So we have detected 10 classes of rices which belong to different area of the rice plant. That may be a leaf or stem or smut disease. So we have done automated system is needed to detect the disease with the severity level. So we have identified the different disease in the rice plants. So these are the bacterial, virus, and fungal disease in the rice plants. So they are in the following parts like leaf, stem, or sheath. So these are the different diseases where we have tried to find out whether the plant is having any one of these diseases. So we are trying to find out the multiple diseases in a single plant. So these are the some of the figures. So like stem right disease is in the stem, so it may be a fungal infection, and the plant look like this. Black lesions are formed on the outer leaves, and these are like sheath disease, like fungal disease, blight, or rot, or spot, or rice sheath. So these are the most commons. That is a rice leaf disease when there is a bacterial leaf stick, leaf smut, or leaf blight. So these are the different problems in the previous automated systems. So first is the binary classification. Binary classifications means most of the work in this area try to find out whether the plant is having some kind of disease or not. That is a binary classification. That is whether the plant is having a disease or not. Only that is, or whether it is healthy. But we are trying to find out the multiple disease, a part of it, severity level also. So it only detects the leaf images, not the stem and sheath of the plant, and it cannot detect multiple diseases in one image. And are also very no much work is done on the severity level. So we have proposed a secular softmax based positional encoding deep convolution neural network based rice plant disease detection to consider all the parts of the rice plant for efficient detection and to identify the severity level by percentage of infection without fuzzy rules, to perform a comparative analysis of proposed techniques with the already existing techniques. So this is a block diagram of the proposed methodology. We will explain one by one all the blocks. So first of all, we will take the input image, then we will do the contrast enhancement, then we will do the background removal, then the segmentation, and segmentation part we will differentiate the stem, sheath, and leaf part. Then we will do color transformation, and then the clustering will be done, so where we will try to find out the healthy and disease parts. Then we will try to find out the feature extractions by using some classification method. So in this feature extraction, so we will try to find out the plant is having which kind of disease. So as I have told you earlier, we are trying to find out the 10 disease in the rice plants. And finally, we will try to find out the severity prediction, POI, with the fuzzy rules. So the data set for the images of the rice plant is taken from the open sources. So the images are taken from the Kaggle, GitHub, Plant Village, and some images are taken from the Google. So rice leaf disease data sets have divided into two classes. One is healthy and unhealthy images, and then unhealthy disease further divided into 10 classes. That is a different kind of disease where we try to find out. So these are the some of the samples of the healthy rice leaves, how the healthy leaf should look like. And this is a sample of unhealthy rice leaves. So our first step is contrast enhancement. So it will improve the visual appearance of the image. We have used the CLT DPHE, that is a correlated log transformed double plateau histogram equalization algorithm. The first step is, so these are the different steps where we're trying to find out the histogram, then we are trying to find out the upper and lower threshold value. Then finally we have for in the step 3, we have used the enhanced pixel intensity is calculated based on the following condition, like if the value is more than upper threshold, then we have used lambda minus TU, that is, uh, and the major problem in this enhancement is the zero pixel matrix, that is the third one. So up till now, no one has done in the contrast enhancement of these plant disease or any kind of this to try to find out the zero matrix pixels. But we have also tried to work on this zero matrix pixels also. So I will explain just after this. So the correlated log transform is performed to handle the zero metric pixels and reduce the noise. Because if we will not reduce the zero in this equation, so then what will happen? So there will be some noise is there. So that for that purpose, we have applied CLT method also. And for the identified zero metric pixels, a logarithmic transformation is applied by the equation shown in this. So we have compared with the available enhancement algorithms. So we have used the for comparison CLT DPHE. We have compared with DPHE, that is double plateau histogram equalization. We have compared with contrast limited adaptive histogram equalization, and then AHE, that is adaptive histogram equalization, and finally the histogram equalization. So these are the different methods which are used for the enhancement. So we have used these, we have compared our result for the enhancement purpose with these available in literature. So the matrices used for comparisons are PSNR, that is peak signal to noise ratio, mean square error, root mean square error, structure similarity index methods, and mean absolute percentage error. So firstly, what is the mean square error? The mean square error is calculated by finding the difference between the actual pixels of the image and the predicted pixels of an image. So here the error is equal to, that is the actual, we will differentiate and then the summation is done. So as I have told you that we are comparing with these algorithms, the first uh, uh, here this bar chart shows the proposed CLT DPHE method, and there is error mean square error is 6.3265. So we have compared with the other methods. So it is less than the other enhancement algorithms. Then for the other matrices is the PSNR. It computes the peak signal to noise ratio. It is used for the quality measurement. So higher the value of peak signal to noise ratio, the higher the results are. So here the proposed CLT DPHE method is again compared with the others technique available in the literature, and the peak signal to noise ratio error we have found in our method is 31.3278, which is more than the other available. We have used root mean square error. That is another type of error measuring technique. It evaluates the error magnitude. And for the proposed CLT DPHE, it was 3.3218, and it is again less. So the less the mean square, root mean square error, the better is the result. And then the structure similarity index method is the perception based model. It measures the similarity between the two images, the original and the recovered. So the higher the value of SSIM means that there is a very much similarity between the actual and enhanced image. So the proposed CLT DPHE method gives the result 0.9011. So which is again more than the existing methods. So the next step is the background removal. So the background removal is a digital image processing procedure that can be used to classify the parts of image in terms of unwanted and interested region, or background and foreground region. So because when we take the pictures of a rice plant, so there are some background is also there. So we want to filter that part out. For that purpose, this background removal step is needed. So we have used SCGMM, that is Shannon entropy based Gaussian mixture method algorithm is used. The GMM effectively captures the statistical characteristics of the background in the complex scenes with the varying illumination and motion. So SC calculation on the probability distribution function with respect to the intensity level. So what we will do, so actually we have to either decide whether the part is a background or foreground. So if the intensity entropy, the value is more than the threshold value, then we will make it as a foreground. So if it is less than that threshold value, so we will put into the background, and then the background part is filter out. The next step is the segmentation. So it separates the parts of rice plants, namely the stem, sheath, and leaf are segmented, because we are trying to find out the disease in every plant, every part of the rice plant, not only in the leaf or one part. So that's why we have to differentiate between, we have to segment them in the different parts. So this segmentation enables the individual analysis of the stem, sheath, and leaf, which helps to understand their distinct characteristics and potential disease presence. The CDSO ARG, that is a construction dove swarm optimization based average region growing algorithm, is utilized for the segmentation purpose. So we have again compare these segmentation algorithms with the other segmentation algorithm available in the literature. So then we have find out that this CDSO ARG algorithm is giving best result than the other results. For this purpose, dice score matrix is used to find out. So dice score is a measure of the similarity between the predicted and the actual data. So it is equal to 2 multiplied by number of the common data. So higher the dice score, better the algorithm. So here we have compared over this CDSO ARG algorithm with ARG, SegNet, and ResNet algorithm. So which are the other popular algorithm for the segmentation. So we have find out that this proposed CDSO ARG algorithm is giving better result than the others available in the literature. That is, it is giving result 0.892. Then next step is the color transformation. So in the plants, the leaf vein is different in intensity and disease spot is different in the color in comparison to plant leaf. So because every part has a different color code for the to find out the disease. So color transformation is necessary as each plant disease has some specific color. So each color space represents some different information about the image color. So here the three color transform models are considered. That is, first is YCB-CR model, second is HSI model, and third is the CIE-LAB color model. So these color transformations are performed separately for each color space, resulting in three transformed images. The pixel values from each transformed image are merged and then provides unique color patterns associated with different parts of the rice plants and their disease. And the next step is clustering. So this clustering process groups the similar pixels together based on the color characteristics. The aim of this clustering phase is to distinguish between the healthy region and the disease affected regions. So we have used SSK means, that is Sorensen and Silost based K means algorithm is used for this clustering purpose. So after clustering, we obtain two cluster. One is healthy and another is disease. So this kind of work is already done in literature. But what we have done, we have again clustered the disease part into the 10 classes. So for clustering, so we have to again try to find out the performance of our clustering method by using clustering time matrix. So lesser the clustering time with lesser error, better the algorithm. So SSK means is then compared with the other clustering algorithms. So that is fuzzy C means, and then clustering large applications. So then we have find out that the time which is taken by this SSK means is less. So for every stage, we have tried to find out the best. We have tried to use the best algorithm for that purpose. So for clustering time, we have use this proposed SSK means algorithm. And then the next step is the feature extraction. From the disease clusters, then the important features such as color, shape, location, and texture features are extracted. So it looks simple that only color, shape, location, and textures, but again, there are number of classes in the colors, number of classes in the shape, number of classes in the location and textures, so which I have not mentioned here to make it simple. So by these features, we calculate the area of the disease portion, the number of disease spots, the minimum area and the obtained disease spots, and the maximum area the obtained disease spots. And then again the classification. So image classification is the task of assigning a label or class to an input image. So a CNN is used to special class of neural network that are built with the ability to extract unique feature from the image data. So they do not encode the positional information of the input. So that's why we have again applied a further thing. So to address this limitation, the proposed methodology incorporates a positional encoding layer into the CNN architecture, which was already not there. So we have added a further layer, that is a positional encoding layer. For the disease classification, this research methodology used the scalar softmax based positional encoding deep convolution neural network algorithm. So this methodology considers the positional and encoding layer with the deep
क्योंकि वो
convolution neural
होलसेल
network.
वाले क्या आगे पूछा गया कितना सारे आगे चला गया
So this methodology considers the
किससे
positional
पूछ
encoding layer with the
आजा
deep convolution neural network. So it uses the softmax activation function. The proposed algorithm is compared with the existing classification algorithm. So again, the results are compared with the other methods which are available in the literature. So I think I am audible. Okay. So this is again the block diagram of the CNN which we have used to apply. So here we have given different scores. You can see that to find out the kind of disease. In the last, if like score is 0.12, then it is a rice stem root, 0.1, then rice shell spot. So we have tried to find out the disease by giving them score. So these are the other layers which are available. One is the input layer, positional encoding layer, convolution layer. So the pooling layer, fully connected layer. So these are the parts of the CNN. So the output layer. Finally, the output layer efficiently classify the disease. The difference between the target value and observed value is called the error value. So if error is 0, then the back propagation process is required. If error is not equal to 0, then the back propagation process is required to optimize the weight values. And finally, when we have find out what kind of disease is having in the rice plant, out of these 10 disease, we have tried to find out the severity prediction. So the severity of each disease is predicted using the percentage of infection value. The severity level is categorized into 3 levels, namely low, medium, and high. So we have given this value. If the PY lies between 1 to 20, we will say that there is a very less infection in the plant. So that is low severity. And if POI lies between 21 to 50%, so it means there is a moderate disease in the plant. And if POI lies between 51 to 100%, then it is the plant is highly infected with the disease. So these results are calculated by using PPV, that is positive prediction value. So that is true positive plus false positive, true positive divided by true positive plus false positive, that gives the PPP value. So the value of the proposed algorithm is 0.988372093 compared to the other existing CNN, DLNN, LSTM and ANN algorithm. So which is more than the other algorithms. We have also calculated the NPV. uh, so that is true negative divided by true negative plus false negative. Again, the proposed method gives better results. So the training time taken by the proposed method is in millisecond. So that is 57005. So however, so when we run on different images or different times, so this time may differ, but again, it is giving better training time compared to CNN, DLNN, LSTM, and ANN algorithm. So these are the again the results which we have uh, used different matrices like precision, sensitivity, recall, F measure, accuracy, and specificity for the proposed method and the other existing algorithms. So and we have find out that our proposed work give better results in almost all of the matrices for this purpose. So here are the some of the screenshot of the proposed work step by step. So as I have told you, we have developed an app or algorithm or application, so which works. So this is the a screenshot of that. So here, like we can see that, sorry. So first of all, we have to select the image from the data set. So then contrast enhancement, then background removal, segmentation, then color transformation, all the steps which I have told you, so are there. So it shows one by one, like if I will show you like first, then the selected image is one.jpg. So this image is rice disease detection. Image was selected successfully. Then if I will click on the contrast enhancement, so it will do the contrast enhancement of the image. Then the background removal. So here you can see the third image shows the background is removed. Then segmentation part. Segmentation is done successfully. Then we will click on, when we click on the color transformation. So it will apply the color transformation. Sorry. So then next step is clustering. So when we'll click on clustering, so it will do a severity prediction is also done. So here you can see that here it has find out the rice disease detection in the last. So it is told that this plant is detected with bacterial leaf stick. So in the next severity prediction is the high severity. So in this way, step by step, it works. So these are the some of the references which we have used for our work. So that's all for today. Thank you very much for your patience listening. So if there is any query, so I'm here.
If there is any query from any of the delegate, please.